I would like to extend a very warm welcome to everybody in that case. And thanks so much for joining us at the New Hampshire Network for Environment, Energy, and Climate as we discuss some of the science behind the new state climate assessment for New Hampshire. This assessment is a new document. It's just about to be published, literally at the printers as we speak. And we're very much looking forward to getting a sort of a preview of some of the details from two of the primary authors who are with us this evening and whom we are very pleased to welcome. And it's really great to see lots of folks showing up and getting concerned about New England's future climate conditions. We know there are substantive changes coming for New Hampshire, as for the rest of the world. And I think we can agree it's better to be prepared than not. So we're very glad to see lots of Granite Staters and other denizens of New England with us tonight. Thank you all for coming. The New Hampshire Network was established just a bit over a year ago with a goal of facilitating communication among folks in New Hampshire who are concerned about issues regarding environment, energy, and climate, and to help raise the profile of these issues in policy discussions at the state level. One way that we're doing this is by holding meetings with the general public once a month on the second Monday of each month, each time focusing on a different aspect of what's happening in environment, energy, and climate in our region and in the world. I am Reinmar Zeidler, member and co-manager of the New Hampshire Network. I live in Cornish, New Hampshire, and I teach classes in conservation biology, sustainability science, and climate change at University of Massachusetts in Boston. I will now move to our next slide. On this slide, you see the title of this evening's proceedings. I will introduce each of the speakers individually before they speak. And before that, just a few housekeeping items. First and foremost, let me acknowledge that this event takes place in Indakina, the ancestral homeland of the Abenaki, Pennacook, and Wabanaki peoples, past and present. We acknowledge and honor with gratitude this land, the waterways, and the people who have stewarded Indakina throughout generations. Secondly, and also importantly, please let's all remember that this is a Zoom meeting, not a webinar. So everyone should be careful to stay on mute the whole time to guard against echoes and other kinds of potential disturbances or distractions. Thank you very much for doing that. Then thirdly, let's see, one of the main purposes of the event, in fact, of the whole network, is to offer opportunity for questions and answers on the topics at hand. So we welcome them. Please drop your questions in the chat function, and I, along with my co-managers, Susan Richmond and John Gage, will field as many of them as possible during the time that we have. And finally, this program is being recorded, and everyone who registered will receive a link to the recording in email as soon as it's available. It'll also be available on our website. I think there was some talk about setting up a YouTube channel, so we will see, but in any case, that will be available shortly for anyone who wants to catch up on things they missed. And now, without further ado, I'd like to introduce the first of our speakers this evening. Dr. Mary Stampone wears two professional climate hats. She's New Hampshire's state climatologist and is also associate professor of geography at UNH, University of New Hampshire, where she teaches courses on weather, climate, and natural hazards. Her research focuses on regional climate variability and change, and on methodologies for monitoring climate systems over time. She's also published extensively on changing public perceptions of climate change and is co-author on the new state climate assessment. So all of this makes her just the perfect person to have on this call. Dr. Stampone, I will now stop sharing and please go ahead and start in.
Okay, can you hear me all right?
We hear you very well, and we can see your slides.
Fantastic. All right, well, thank you for the introduction, and to all of you for being here, and happy Pi Day. To get us started tonight, I'm going to take a little bit of time to summarize some of the key indicators of 20th century climate change, so past climate change, here in New Hampshire, focusing on statewide temperature and precipitation that are all going to be part of the upcoming New Hampshire State Climate Assessment Update. And so I'm not going to go into detail on the local scale change, but we do have that information. I'd be happy to talk about it after the presentation. Okay, so to start us off, just a little bit of a summary here about New Hampshire climate. So New Hampshire is located within the Northeast climate region, where the distinct seasonality supports a diverse natural landscape adapted to the extremes of cold, snowy winters, as well as the warm to hot, humid summers we tend to have. New Hampshire's proximity to the coast and location below the confluence of three major storm tracts result in a humid climate and relatively uniform precipitation distribution, averaging about 43 inches annually. However, we all know local temperature and precipitation patterns vary from the state average due to both distance north and inland, as well as elevation. So at daily scales, New Hampshire's weather is highly variable and capable of producing severe conditions, including extremes in both warm and cold temperature, as well as precipitation that can result in floods as well as drought, which can both actually occur at the same time, which is what kind of happened last summer. So as the dynamics of a changing global climate system continue to impact the Northeast, the characteristic climate of New Hampshire will inevitably change. Since the beginning of the 20th century, New England has become warmer and wetter, with an increased occurrence of both warm and wet weather extremes. So because temperature and precipitation trends are closely linked to Earth's climate system through the hydrologic cycle, increases in precipitation can often accompany increases in temperature because warmer air can evaporate more moisture from soil and vegetation. So all things being equal, regions like New England that are near warm offshore ocean currents can expect to see increases in the total amount and intensity of precipitation as temperatures continue to rise. This is in contrast to the West, which is going to get drier as temperatures rise. So now already, we're seeing changes in regional hydrology that are resulting from this combination of increases in temperature, heavy precipitation, and associated runoff, both of which are impacting water availability and quality, particularly in the late summer. And other climate change impacts, such as reduced snowfall and winter recreation, increased heat-related injury and illness, an increase in heavy rain and flood events, the spread of invasive species and vector-borne diseases, all of these together pose a significant threat to New Hampshire's economy and its residents' quality of life. Now, to assess past changes in New Hampshire's climate, trends in state average temperature and precipitation were evaluated along with local scale trends and variability in daily meteorological data. The trends in average statewide temperature and precipitation dating back to 1901 were quantified using data from NOAA's US Climate Divisional Database. And then at the local scale, variability in trends in both average as well as extreme temperature and precipitation were quantified using daily meteorological data from 10 of the state's daily global historical climatological network stations, those GHCND stations. So measures of extreme precipitation and temperature will include things like the number of days per year exceeding some specified threshold, like 1 inch of precipitation in 24 hours, or maximum temperature of 95 degrees Fahrenheit for the high. And so trends in 32 of these types of climate indicators for 1971 to 2020 were computed at all 10 stations to quantify recent change, while the long-term records at Durham, Hanover, Keene, as well as Berlin were evaluated for change since the early 20th century. And so all of these, or the following slides here are going to highlight some of the most important changes that are observed to date. And it's worth noting all of these trends were calculated and tested for significance using non-parametric statistics. And trends are considered significant at the 95% confident interval. And you'll see those values are going to be outlined and in bold. All right, so to start off, let's kind of take a step back here and look at the regional scale, where the Northeast here is warming faster than the US as a whole, and seasonal temperature differences are actually decreasing in response to a warming rate during winter that is 3 times faster than summer. Now, much of the winter warming has occurred since the 1970s and has resulted in an overall milder cold season with fewer severe cold events, more days above freezing, and fewer days with snow on the ground. And these trends are expected to continue, with annual average temperatures regionally expected to reach over 3.5 degrees of Fahrenheit above the pre-industrial era just in the next 15 years. And it's worth noting that this is the largest expected temperature increase in the contiguous United States and would occur about 2 decades before global average temperatures reach this same milestone. Now, focusing in on New Hampshire, the graphs shown here represent the continuous record of state averaged both mean annual maximum on the left and minimum on the right for temperatures over the past 120 years. Now, of course, there's considerable year-to-year variability, but significant trends in both occur over both the 20th century as well as over the more recent 50-year period. Now, overall, there was a significant warming trend in state average mean annual maximum temperature of over about 2 degrees Fahrenheit during the 20th century, with a near doubling of the warming rate happening since 1971. Additionally, there's a significant increase in mean maximum temperature since 1901 in all seasons. So this is the annual, but we also saw significant increases seasonally, with greater warming occurring during both the fall and winter seasons. So we're seeing that increased warming during the cold season. Now, while our days warmed, the rate of warming was greatest at night, with a significant increase in mean annual minimum temperatures of about 3.5 degrees Fahrenheit since 1901. And again, much of this warming occurred since the 1970s. And so here again, you see there was a significant increase in seasonally average minimum temperatures over the 20th century. And again, greater warming during the cold season. So we're seeing the pattern kind of show up of warmer cold season, warmer nights. And overall, mean annual temperatures across New Hampshire increased by an average of 3 degrees Fahrenheit since 1901, but that warming occurred at a faster rate, again, since 1971. Now, focusing on winter, we have seen warming across all seasons, but the rate of warming was greatest during the fall and winter seasons, particularly at night. So overall, the greatest seasonal warming rate occurred in the winter season minimum temperatures, which are shown here, with winter nights warming at a rate of about 0.5 degree Fahrenheit per decade since 1901, increasing to a rate of over 1 degree Fahrenheit per decade since 1971. And so as our winters warm, we've seen a decrease in the frequency and severity of cold extremes, along with an increase in the number of thaw events within the season. So for example, we've also seen at all 10 weather stations that we evaluated, they show an increase of about 6 to 14 degrees Fahrenheit in the temperature of the coldest night of the year. And all but the weather station at Colebrook recorded a decrease in the number of days with a minimum temperature below 0 Fahrenheit and number of days with minimum temperatures below 32 degrees Fahrenheit since 1971. And so a result of all of this warming, there was a 10% decrease in the number of heating degree days per year, which indicates that there's a reduction in the energy required for indoor heating during the cold season. However, this decrease in energy for heating associated with the heating degree days is actually smaller than the increase in the number of cooling degree days, which occurred during the warm season. So this kind of tells us that summer cooling needs are increasing as the winter heating requirements are decreasing. So in addition to fewer cold extremes, milder winters are associated with more days above freezing and therefore less snow on the ground. So for several decades, the New Hampshire Department of Environmental Services have maintained a set of snow sampling sites across the state in order to better quantify the amount of water, so amount of liquid water stored in the seasonal snowpack, which is called the snow water equivalent. And so here we're looking at snow water equivalent observations across 5 different sampling sites within the Lake Winnipesaukee watershed. And 3 of the sampling sites here, along with one site at Owlbrook, which is in the Squam Lake watershed, indicates significant declines in annual maximum snow water equivalent, which is ranging from a decrease from 59% to 91% compared to the historical mean value. So now the 2 other sites, the 2 other sites, they're the Mary Meeting and North Wolfboro sites, as well as other sites in a few of the other watersheds that are sampled, show non-significant decreases in annual maximum snow water equivalent. None of the sites that were sampled showed an increase, significant or none, over the period of record. Now, similar to reductions in snowpack, we're also seeing lake ice out dates that are happening earlier in the season. Now, lake ice out dates are frequently used as an indicator of winter early spring climate change due to the close correlation with surface air temperature in the months that are right before the ice breakup. And so this is showing records of lake ice out on Lake Winnipesaukee, which actually began in the late 1800s, but here we're showing 1900 to present. And most of these dates, the method for determining ice out can vary, but here on Lake Winnipesaukee, most of the time it's declared when the MS Mount Washington cruise ship can safely navigate between the different port stops. And so in this record, 3 of the earliest ice out dates have occurred since 2010, with the earliest being March 18th back in 2016. And then overall, ice out dates trended earlier over the past 50 years, with ice out occurring on average 8 days earlier at Lake Winnipesaukee, which is consistent with as many as 28 other long-term ice out records from New Hampshire, Maine, and Massachusetts. And so overall, warmer winters with less snow and a longer winter-spring transition period are expected to have negative consequences, not just on recreation industry, but also on northern forest ecosystems, which again can then impact other rural industries, as well as increasing our exposure to vector-borne diseases that are prevalent during the warmer season. Now, switching over to precipitation here, precipitation measurements, both liquid and frozen, are commonly used indicators of climate change. And across New Hampshire, total annual precipitation has increased by as much as 19% since the turn of the 20th century. Now, these changes are attributed to an increase in the amount of rain falling or intensity during one-day or multi-day precipitation events. And the frequency of these extreme precipitation events has increased regionally since the 1990s. There has been several recent studies that indicate much of the increase in extreme precipitation over the past 25 years, at least as far as the Northeast is concerned, is due to tropical cyclones in the fall, so an increasing in intensity of those storms, as well as frontal storm systems that occur throughout the year. Then, in addition to extreme precipitation, recent years have also been punctuated by periods of moderate to extreme drought development during the warm season. So while we are overall getting wetter, we are still at risk for warm season droughts. And then in addition to overall precipitation, there was an observable increase in precipitation in winter, which is consistent with the regional pattern. And with warming winters, the proportion of winter precipitation falling as rain has already increased, again, to those milder temperatures and warming during the winter-spring transition. And all of this has led to earlier snow melt-related runoff in areas of the Northeast, including New Hampshire, with substantial snowpack. So the graphs I'm going to show here provide a continuous measure of total annual precipitation averaged over all of New Hampshire since 1901. And like temperature, there's considerable year-to-year variability in total annual precipitation, but significant trends in both annual and seasonal precipitation are present over the 20th century. So for total annual precipitation in New Hampshire here, it has significantly increased by about 8 inches since 1901 at a rate of 0.67 inches per decade. Seasonally, the largest significant increases in precipitation have occurred in winter, with some modest but still significant increases during fall and summer. While there are no significant trends in annual and seasonal precipitation over the most recent 50-year period, the summer season has had the largest total increase since the year 2000, with 5 out of the 10 wettest summers on record occurring after 2004. And of course, the past 2 summers have been some of the driest on record. So, in addition to this, there are important trends in daily climate indicators that are coherent across most of the 10 locations that we looked at for local trends. So for example, there was an increase in the number of precipitation events per year exceeding 1 inch in 24 hours. So across the state, we've seen an increase there. And we've also seen an increase in the amount of precipitation on the wettest day of the year at most of the weather stations across the state. So we're seeing an overall trend of total annual precipitation. Much of it is coming in these singular large events. But I think what is most concern to a lot of folks are these extreme events. And so here we're seeing a graph of the number of events exceeding 4 inches of precipitation in 2 or more days. And these are plotted in events per decade over the past 50 years. And so at most stations, we've seen an increase in the occurrence of these events. And although the trends aren't statistically significant, due in part because of the small number of data points, these are still fairly rare events. The increase has been particularly large across the seacoast. So we can see the increase here at Greenland and Durham, as well as at some of the higher elevations. Here we see it, the Pinkham Notch Station. And so overall, this combination of above average precipitation amounts and more frequent extreme precipitation events has, of course, increased the risk of flooding across the state. But then despite the increases in total annual rainfall, we are still at risk for increasingly more intense warm season droughts due to the greater evaporation of soil moisture during dry spells from higher summer temperatures. So we have this extremes on kind of both ends of the precipitation spectrum. And then to kind of wrap this up here, sea level rise is also occurring along our coast. And so based on tide gauge data from CV Island and Portland, Maine, which are shown here, relative sea level in coastal New Hampshire and southern Maine has risen approximately 7.5 to 8 inches between 1912 to 2018, which has resulted in an increase in the frequency of high tide flooding, which occurs when water levels exceed the local high tide threshold, and the inland extent of storm surges. And so coastal communities along New Hampshire coast are already vulnerable to sea level rise, and coastal storm surge along with high tide flooding events have already damaged infrastructure, caused road closures, and overwhelmed our stormwater infrastructure. So as the world warms, the additional heat added to the atmosphere and ocean will likely lead to stronger storms and more extreme hot temperatures. And so here in the Northeast, we're particularly at risk because much of our infrastructure was not designed for today's, let alone projected future climate conditions. And they're all nearing the end of the utility period. And so beyond weather, urbanization increases heat as well as runoff, resulting in an increase in the magnitude and duration of heat waves and flooding. And then the increased risk of flooding and extreme heat expected with continued global warming threatens critical utilities and transportation infrastructure across the state. And Cameron Wake will be talking a bit more about the future projections and what this might mean or have in store for the state of New Hampshire. But so to wrap up the observations, we can already tell that the increasingly erratic and extreme weather of a warmer climate is already here and is already disrupting lives and livelihoods across New England and New Hampshire. Rural northern New Hampshire residents who are already stressed by isolation and declining economic opportunities are particularly vulnerable to the changes in weather associated with a warmer climate. From hurricanes like Irene and Sandy to our winter bomb cyclone nor'easters, along with record high tides, the coastal region has already seen the impacts of severe storms. And then disruption to services, unequal access to resources, all disproportionately impact those who are already vulnerable, including low-income and Indigenous communities, some communities of color, children, and the elderly. And overall, higher temperatures, increasing air quality risks, more frequent and intense extreme precipitation, weather and climate-related events, coastal flooding, disruption of ecosystem services, and all of these other changes are increasingly threatening the health and well-being of New England residents. So in sum, climate change is happening now, and it is a real and immediate threat to the unique seasonal character, storied environment, and sense of community here in New England. But we still have time to address it. And Cameron Wake will take it from here to discuss some of the impacts that are in store for us, depending on how we address what has already happened. So do we want to go on, or do you want me to answer questions first?
Thanks, Mary. I think what we'll do is we'll take the questions at the end. So folks, anybody who has a question, please note them down and include them in the chat. And I just wanted to, introduce Cameron. I know you're going to be using the same slide deck. That's fine. But let me just say a word or two so that people know where you're coming from. Dr. Cameron Wake is a research professor at the Institute for the Study of Earth Oceans, and Space at UNH, University of New Hampshire, and also the Josephine Lamprey Professor in Climate and Sustainability at the UNH Sustainability Institute. And he has been exercising a research program over some time now, exploring the dynamics of regional climate change through looking at Arctic ice cores, I think also ice cores from Central Asia mountains, and other historical data. And he also helps to lead Climate Solutions New England, which is a collaborative effort to build resilient, low carbon communities in our region. And it is great to welcome Cameron Wake, Dr. Wake. And he is, of course, I think the principal author on the new climate assessment for New Hampshire, and has also participated in IPCC assessments. So Dr. Wake, go ahead.
Thank you very much, and it's great to be here with you. A small correction, actually, Mary Stampone is the lead author on this assessment. I've certainly led other assessments, but she's the lead on this one, and rightly so. So great to be with you tonight to sort of continue this discussion on climate change. And Mary, if you could just flip to the next slide. So Mary has taken you through many of the details of how climate has changed in the past. And if you missed the message on her last slide, I'm just going to repeat it, right? Climate change is already here. It's already affecting you. It's already affecting our economy. It's already affecting our ecosystems. And in some ways, we now have a taste of what climate change is going to be in the future. So I'll go through a series of graphs and explain how we've projected how our climate's going to change. But essentially, it's going to be warmer in the future. It's going to be wetter. More of that rain is going to become in fewer events. So we're likely also going to have more drought because our summers are going to be a lot hotter. And our winter, our winter season is going to change the most. It's going to shorten. There's going to be less snow and less cold. And all that is going to continue to have significant impacts on our quality of life, on our ecosystems, on our economy, and on our mental health. So what I want to start with here is talking about how it is we go about projecting the future. And so it's really challenging because we don't know what our economy is going to be. And we don't know how sort of global events are going to influence how much fossil fuel we burn. So instead of trying to predict how climate's going to change, what scientists have done instead is developed a set of different scenarios of how much greenhouse gas there's going to be in the atmosphere based on human activities, as well as changes in our natural ecosystems. And then we use that as a guide to run these big global climate models that then essentially provide us with a measure of how our climate is going to change. And so what we've done here in New Hampshire is we've looked at the historical record and we've compared the global climate model output to the historical record, and we've developed statistical relationships between local meteorological data and the grid cells that are provided in the global climate models. And we develop those statistical relationships. So as we run the models in the future, we use those statistical relationships to actually statistically downscale the global climate model output to provide an estimate of how our climate might change very locally in particular stations, or in this case, we're going to talk more about the state of New Hampshire. When the report does come out, we do have these statistical downscale projections for all of those 10 meteorological sites that Mary started out with. So what we have here, what you see on the screen is essentially the black is the observational record that Mary was talking about. And then in the blue, you see one projection on how temperatures might change under a lower emission scenario. So that lower emission scenario we call an RCP 4.5. You don't have to worry about that, but it's essentially a world where where global warming goes up to almost 2.5 degrees Celsius by 2100. Right, so it's above that, far above that 1.5 degrees Celsius that we should be sticking to. But this is sort of the model output that we had access to. So there you see one. Can you hit next slide? So right, you've got the observations from the climate data set. Here's one model. Hit it again, Mary. And then essentially what we did was we analyzed output from 29 different climate models. And therefore, what you see here is all 29 models in the light blue, and then the dark blue represents the ensemble mean of all those 29 models. And that's essentially what we're going to be focusing on in the projections. And there's quite a bit of research that shows that the ensemble mean tends to be the best estimate of how climate's going to change in the future. You'll also note that there's an area of gray from 1980 up to 2010, and 1980 up to 2005. And that's the period over which you can sort of, we have the observations and we also have the model. And you can see that there's a pretty good relationship there. So we're confident that the model is capturing the local changes. And then finally, that blue is under the low emission scenario. The red is under the higher emission scenario. We call that RCP 8.5, but that's in a world where temperatures rise to 4.3 degrees Celsius. And so temperatures so far have warmed globally around 1 degree Celsius, right? So there's a really big difference between the lower emissions and the higher emissions scenario. And that's one of the main messages from the presentation tonight, is that we are going to have to adapt to a warmer world in New Hampshire, but how much we have to adapt to is fundamentally driven by how much greenhouse gas human activities put into the atmosphere. And we sort of have a decade to turn that global energy system around. All right, next slide, Mary. So here we're looking at sort of similar graph to what we just showed you. And we've got New Hampshire annual maximum temperatures on the left and minimum temperatures on the right. And so a couple things here are really important. You'll notice, hit the next slide, Mary. You'll notice that in both the minimum temperature and the maximum temperature, by the time we get to 2040, there's no difference between the low emissions and the high emissions scenario. All right, so we are headed for a world in New Hampshire where temperatures by 2040 are going to go up 2.2 to 2.3 degrees Fahrenheit average, right? Minimum and maximum temperatures. That is an amount of warming that we are going to have to adapt to. So there's very little uncertainty about how much warming there is. The second major point is that if we can turn around our energy system and invest in renewable energy and invest in energy efficiency, we can be on that lower emissions scenario, which results in something on the order of 5 degrees Fahrenheit, a little more than 5 degrees of Fahrenheit warming by the end of the century. Conversely, if we just continue to rely primarily on fossil fuels and do more fracking and mine more coal, keep buying oil from Russia, we're going to see temperatures, both minimum and maximum temperatures, go up by 9 degrees Fahrenheit, which is going to be, if that happens, it's going to completely change the character of our climate system across New Hampshire. And it would be a climate system that is far more similar to something that exists in the southeastern US than exists in New Hampshire today. And so one of the big messages here is that globally we have a choice on how much our climate changes. And what we really need to do is not only be on the low emission scenario, but we actually have to figure out how we get to net zero emissions by 2050. I'm not going to talk a lot more about that, but we can hash that over in the question period if you'd like to. Next slide, Mary. So we've also, just like we did for the historical record, we've broken this down into seasonal information. And what I'm showing you here instead of the time series is I'm showing you maps of the amount of warming across the entire Northeast, which begins to show you that it's, at least in terms of temperature, we see sort of very broad, consistent patterns across the whole region. One of the things I can tell you is that in terms of temperatures, our winters are going to warm faster and our nights are going to warm faster. So similar to what we've been seeing already, we're going to see the greatest amount of warming in wintertime minimum temperature. So warmer winter nights. So why do you care? It's like, hey, I have to put less wood on the fire. But really, those cold wintertime temperatures have been really good at keeping a whole set of pests and weeds out of New England. And that's actually going to continue to decrease. But some of the pests we're dealing with now that are particularly problematic are the hemlock woolly adelgid that is affecting our hemlock trees, they're killed off by cold wintertime temperatures. When you don't have those temperatures, you don't kill off those pests. And there's certainly a strong argument that says we're going to see, or the spread of Lyme has in fact occurred while we've had these warmer time temperatures, and significant impacts on our moose population as well because of a different kind of tick. Also shown here in the blue is the low emissions projections, and in the red on the bottom is the high emission projections. So Mary, take us through all three of those. Once again, you can see under the lower emission scenario, by the end of the century, that's the image on the far right, our winters in New Hampshire increased by 6.8 degrees Fahrenheit under the low emission scenario. And under the high emission scenario, right, they increased by 11.5 degrees Fahrenheit. Again, there's a significant difference between the lower emissions and the higher emission scenario. And in the 11.5 degrees Fahrenheit, yeah, go ahead, Mary. In the 11.5 degrees Fahrenheit scenario, I mean, we have significantly lost the character of winter that we have grown up with. Very little snow, very few cold days. Next slide. Another thing we've looked at is what the impact is going to be on very hot days. And so heat waves are defined when you have 90 degrees Fahrenheit for 3 days or more. And so traditionally in New Hampshire, we've had less than 10 days like that per summer. So 10 days out of 90 would be less than 10 days out of 90. And oftentimes, if you're in the middle or northern part of the state, there might be 1 or 2 days that are higher than 90 degrees Fahrenheit. So this is the same set of graphs. You can see the historical period, and then we're going through sort of the early to the mid to the late. And if you look again at the end of the century, 2070 to 2099, you can see there is an increase in the number of warm days. And so we're looking at something on the order of 20 to 30 hot days, sorry, not warm days, hot days per year. So we see like a third of the summer in hot days. Under the high emission scenarios, we're looking at more like 60 to 70 hot days per summer, which essentially means that more than half and maybe 2/3 of our summer is a heat wave. So again, under the low emission scenario, there is a change in our summer hot days that we're going to have to adapt to, but it's much higher under the high emission scenario. And again, why do you care about this? Because heat waves results in significant premature mortality to those who are most vulnerable, the young, the old, the sick, and the poor. And so as we have these more hot days, we're not adjusted to that. And so it's going to have significant impact on human health and also on our ecosystems. And as Maria has suggested, it's also going to have a significant impact on drought. And I'll talk about that in a minute. Next slide. So we also looked at, just like Mary did, or just like we did for the historical period, we also looked at the future of precipitation. And you can see that the precipitation impact, the precipitation changes are significantly different than what we saw with temperature, where the high emission scenario and the lower emission scenario were very different. So we see very little difference in how precipitation changes under the high emissions or the low emission scenario, right? There's going to be, with more greenhouse gas in the atmosphere, the globe is going to heat up. And for all those reasons that Mary talked about early on, we're going to see an increase in moisture in the atmosphere. And so we're going to see an increase in precipitation in the mid latitudes in coastal areas like New England. And so what we see is really just modest increases in a mean annual precipitation. So in some ways, this is good news, is that we are going to continue to have fresh water in New England. There's all sorts of changes that are coming, right? More rain, less snow, more flooding as a result of more extreme precipitation I'll talk about in a minute. But overall, we're going to have fresh water. That's not the case for the western part of the country that are already experiencing a mega drought. There are going to be challenges associated with this water. But you can see we're looking at sort of, about a 15% increase in precipitation. Hit the button there, Mary. The challenge is that we see that much of this precipitation increase comes in extreme precipitation events. So this is just one example of those graphs. And what we're showing here on the bottom axis is what the average number of 1-inch precipitation events has been at the 10 stations across New Hampshire. And then on the y-axis is what the change is. So what you can see in every case, the red is representative of the high emission scenario and the blue is representative of the low emission scenario. So for 9 of the 10 stations, we're going to see more extreme precipitation events. But when we parse out the data this way, we begin to see the changes in the low emissions and the high emissions scenario. In every case that we looked at, we see more extreme precipitation events under the high emissions scenario for 1-inch events, for 2-inch events, for 4-inch events. And what that can lead to is more flooding, especially if we continue to pave over ecosystems, we sort of build up our urban infrastructure, there's more runoff. It really leads to the potential for more flooding. And we've seen that more flooding over the course of the past 20 years. And our expectation is in the future, we're going to have to deal with this. And, you know, New Hampshire is particularly vulnerable from freshwater flooding because we've built most of our towns and cities in valley bottoms. So this is a particular issue that we are going to have to adapt to. So we're going to have more water, but we're likely going to have more flooding as well. And so it's going to be a real challenge to adapt to that new normal. Next slide, Mary. And we are in fact going to have less snow. So this is from research that Elizabeth Burakowski has done, sort of modeling how much snow there's going to be in the future. And what we're plotting here is the number of New Hampshire annual days with deep snow cover, which they just said was 6 inches. So that's not water equivalent. Mary had mentioned before, this is just 6 inches of snow. So how many days in the winter do we have 6 inches of snow on the ground? And you can see historically, we were sort of close to 100, right? Average across the state of New Hampshire. The data here is also in lower emissions and higher emission scenarios. So you can see we're seeing that reduction already. By the middle of the century, you can see we're getting down to about half as many days as we had in the historical period. And then by the end of the century, you can see under the high emissions scenario, anyway, we see far, we see a third under the higher emission scenario, but about sort of close to 50 days under the low emission scenario. We see, and so why does this happen? Because less of the precipitation is falling as snow, because we see this significant increase in warmer winters. This is also going to have other effects. We're going to see shorter, earlier ice out dates, so shorter periods of time with ice on lakes, and probably more periods of time with dangerous ice on lakes. Warmer nighttime temperatures are also going to reduce the capacity for snow areas to make snow. And we're going to see earlier snow melt, so that we're going to see those we're going to lose our snowpack earlier in the year, which is going to drive potentially both flooding as well as changes in the ecosystem. And then there's this additional flood risk, which is really hard to measure. But if you have cold temperatures and then a really big precipitation event with when the ground's frozen, that leads to really big floods. And what we're seeing is a majority of that precipitation actually increase, that modest increase we see, but most of it happens in the spring. So if it's falling as precipitation on frozen ground, that's going to create particular problems for flooding. All right, next slide. So we also broke the precipitation down into seasonal precipitation. And what you'll see, just hit the button, Mary, is that we see very little increase in summer precipitation. I just said most of it occurs in the spring, so very little increase in summer precipitation. Next, yeah. Average summer maximum temperatures, we see continuing to increase, right? I showed this slide before. We see sort of on the order of a little more than 2 degrees Fahrenheit by 2040, and then somewhere between 5.4 to 9.5 degrees Fahrenheit warming under the high emission scenario. So we see significant summertime warming, but very little change in summer precipitation. So you've already figured out what this means, right? Is that we don't have any more inputs of moisture, But with warmer temperatures, we have many more exports of moisture through evaporation and evapotranspiration. So while it's difficult to analyze this completely quantitatively, our expectation is that we are going to increase the number of short-term droughts that we have, particularly in summertime, not because of decreases in precipitation, but because of increases in evaporation and evapotranspiration. And in some ways, what we've seen over the course of the last 5 to 6 years with those sort of summertime droughts that we've had are a window into what we expect to happen in the future. So not so much annual drought, but these shorter summertime droughts, which have already had significant impacts on the ability of people who are off sort of city water to pump water out of their wells, for example. Been a significant challenge. And so we expect that is another issue that we're going to have to adapt to. So it gets a little complicated, right? We're getting slight increases in precipitation, but because the temperatures are going up so much, we expect to see this increase in summertime drought. Also going to have significant impacts on ecosystems. Sorry, go ahead, Mary. And then last but not least, I think we're keeping right on time here. Mary showed this slide. This comes from this is a different assessment that both Mary and I were authors on for coastal flood risk that we published back in 2019. And you've got that historical data that Mary showed you from sort of the early 1900s up to 2018, 2019. And then we've got projections of how much sea level is going to rise in the future. So over the last century, sea level has gone up about 8 inches, and we're already feeling the impacts of that, right? More clear sky flooding, and when we have big storm surges, quite a bit more area getting flooded. As we go forward in time, we haven't provided one estimate of how much sea level is going to rise. We've provided sort of a probabilistic outlook on this. So what's the probability that sea level will go up by so many inches or so many feet? And so hit the button, Mary. So what you see here is in the blue is what the likely estimate for sea level rise is based on all the processes that drive sea level increases. So that's global sea level rise as a resulting of warm water, which decreases the density of water, makes it fluffier, so it takes up more volume, of Greenland and Antarctic ice sheet melting and calving into water, of alpine glaciers melting, of relative sea level rise, of coastal subsidence. Our coast is continuing to sink here in New England. So we've taken all the dynamic changes in ocean circulation, taken all those into account. And what the analysis shows is that in terms of the likely range, 67% chance that sea level by 2050 is going to go up by about a foot, and by 2200 is going to go up by about 2 feet, give or take a few inches. So that's what we have to start preparing for. But you also see in the red, you see something that's a 5% probability. So that's a 1 in 20% chance that sea level by 2100 might go up by 4 feet. If you look at the 1% probability chance, the 1 in 100, right, sea level might go up by 5 feet. And then there's a 1 in 1000 chance, that's the 0.1% probability that sea level might go up by 8 or 9 feet. So why did we do this? Why are we confusing everybody with all these probabilities? And the reason is because in terms of how society responds to that, it's really important first to identify what your risk tolerance is. So how tolerant are you to sea level rise? If you're building a sandcastle on the beach, you don't care. If you've got an oyster shack on the beach, well, you can probably just deal with the likely range of 1 to 2 feet. On the flip side, if you are at the Portsmouth Naval Shipyard, if you're talking about I-95, Route 1, a wastewater treatment plant, a high school that serves as a refuge during emergencies, you need to start thinking about the fact that you have very little risk, very little tolerance for risk. And so that you might want to be thinking about that 1 in 100 or 1 in 1000 event as you develop that infrastructure. So coming back to where sort of Mary started about infrastructure, we need to start thinking about our infrastructure and the risk of flooding, both from coastal flooding and from freshwater flooding, and adapt it to match the new climate normal. Next slide, Mary. So I just wanted to end up by perhaps seeding our conversation based on the questions you have. But really, in terms of addressing climate change, there's two big strategies. There's mitigation and adaptation. And in a climatologist, a climate scientist world, mitigation is reducing the amount of greenhouse gas we put in the atmosphere. And the Intergovernmental Panel on Climate Change has suggested, recommended, strongly recommended that we need to essentially get to net zero emissions by 2050, which means that any carbon dioxide we do put in the atmosphere from burning fossil fuels gets taken out of the atmosphere, either through sort of the biosphere, through being absorbed by the ocean, or maybe even through carbon capture efforts. Adaptation are all the things that we have to do to adapt to a new climate. And I can tell you the most important adaptation strategy is to reduce the amount of climate change that we have to adapt to, which means we have to pursue the mitigation strategy. So these two, while we often separate them, are fundamentally linked. We have to do both things at the same time. And because we haven't acted on this issue rapidly enough over the course of the past 3 decades, we have to act really fast right now, especially on the mitigation front. I would also argue that climate change is the innovation opportunity of the 21st century, not just from the technical aspects of renewable energy, but about the way we organize our society and we deal with those who are most vulnerable. It really requires a transformational change, but one that can, I think, can knit society much more closely together. And to do that, we need collaborative action at multiple levels. Next slide, Mary. And so one of the things I want to leave you with is that do not wait for your government to solve this problem, because they're not going to be able to do it even if they wanted to. So different governments have acknowledged the challenge to different levels and have acted at different levels. And local government, state government, federal government all have a role to play, but it's not enough. They cannot solve this problem. They do not have the resources to solve the entire problem. And so one of my biggest arguments on this front is that we need to act on all spatial scales. We need, in our communities, in our cities and towns, in our state, on regional levels, and national levels and international levels, we have to act on all those spatial scales. And we need every institution to act, right? So absolutely we need government to act. I'm sure with John here, we'll hear about how we probably have to figure out some sort of fee and dividend that the federal government can put in place. That's an appropriate response from the federal government. However, we also need business and investment. We need business and industry to act as well. They are substantial players, and as customers and investors, we need to demand that they change as well. And you can see that many companies are beginning to lead on this topic, and we need them to lead, we need to support them, and we need many more to be with them. We also need the nonprofit world to get engaged, and I can speak on my world in academia. We are trying to provide an example at the University of New Hampshire. We've already reduced our emissions 60% below 2001 levels, while increasing the number of students that we have housed on campus and increasing the number of students that we provide degrees to. And we need individuals and families to act, primarily so they can learn that we can actually reduce our emissions and adapt to climate change, so they can take that knowledge to the other institutions where we work, play, and pray. And so I hope that seeds a broader discussion about where we're going from here, but it's really important that we significantly reduce our greenhouse gas emissions. It's not going to stop global warming, it's going to reduce it enough so that we can adapt to the changes. So why don't I end there and open it up for questions?
Great, thank you very much, Cameron. That was awesome introduction to what's coming down the pike for New Hampshire. Now we have got several people who are monitoring the chat and who have some a list, I think, a short list of questions from among the many. I can see there's quite a few there. I wanted to start it off actually by asking one thing that you touched on briefly, but I think it's something that is often confusing to people, outside this world of modeling, which is we take the GCMs, the global climate models, which are huge, complex models with dozens of factors, probably hundreds of factors. It really describing as best we can the entire global climate system, which is ridiculously complex. You take these huge models, and how do you actually downscale them? I mean, how does that actually work? If you can describe it in simple terms, because New Hampshire is tiny in comparison with the geographic spread of those GCMs, but nevertheless, New Hampshire also has incredible amount of detail and variance within the state. We've got the White Mountains, and we've got low-lying areas, and so how does that kind of variability interact with the huge level of complexity of those models, and how do you manage that when you're downscaling to a small scale? Cameron, go ahead.
All right, yeah, so there's two ways. You can dynamically downscale, which means you have sort of models that run on a much smaller region that are connected to the global climate models, but have much finer grid cells. And so we've done some of that, but that's not what I showed you tonight. What we did was statistical downscaling. So you're absolutely right, Reinmar. The grid cells of which on how global climate models run, basically we split up the surface of the Earth into all these different grid cells that are sort of the size of New Hampshire and Vermont put together. And then we have many layers in the ocean and many layers in the atmosphere. And we solve equations of sort of first principles, conservation of mass and energy between those grid cells. So we get the outputs in these big grid cells. So statistical downscaling is just we take the average for that grid cell, and over a historical period, in our case, 1980 to 2005, we compared the average for the grid cell to the average from a meteorological station. So you could have that average for Portsmouth, New Hampshire, or you could have that average for Berlin, New Hampshire. And then you develop a statistical relationship between the mean value for the grid cell and the mean value on the ground as measured at meteorological stations. And then we make this really big assumption that you just have to make, that everybody in the paleoclimate world that I work with makes, is that you say, essentially, the climate system, even though it's changing, those relationships are going to stay static over time. So that's one of the challenges of statistical downscaling, is that we're sort of still in this climate world. We haven't crossed any huge tipping points. Maybe one or two tipping points, not all of them. And so once you have that assumption, then you can just look at the average value for that grid cell in the future, and you can use that statistical relationship that you've already developed for the historical record to estimate what's going to happen in the future at that location. And I would argue that we're quite confident in the projections of temperature and like mean annual precipitation. When we start talking about really big extreme precipitation events that are sort of far out on the distribution, there's not many events, it becomes more challenging. Mary, I don't know if there's anything you want to add to that. Hope I haven't confused everybody.
No, I think it's potentially helpful. I mean, for anyone who's at least wondering about those kinds of things. I mean, I think it also underlines how important the role of community is in thinking about adaptation, because we can't rely on the modeling to tell us what we need to do. If we're in a community north of the White Mountains, we're going to have a different set of conditions within that average, right, than somebody way in the south or on the coast. So the community activity and awareness and work toward adapting is something that communities need to take on, and I think that's one of the reasons why, Cameron, why you were saying that governments are not going to be able to do all of this. The impacts are far more detailed at a smaller scale than the modeling can be. So I think that's a valuable point. Excellent. So Susan Richmond and John Gage are two of our co-managers at New Hampshire Network, and I think they've got a list of questions that they've taken from the chat. So Susan, do you want to go ahead?
Sure. A lot of the questions I have actually have to do with the implications. So the seacoast region, to what extent are those towns taking this seriously, prepared for it, responding to it, and in particular, the dry cask storage of nuclear waste at seacoast is 12 feet above sea level. How is that being prepared for? So this is more policy than science, I'm afraid.
Yeah, I'll take a stab at that. So I am not privy to the details of what's going on at Seabrook Nuclear Power Plant. There have been a lot of concerns raised about that power plant, and one of them relates to sea level rise. I would argue that for the life of the planet, for the life of the power plant, it's in reasonable shape, right? So I think they're trying to get, somebody can correct me, a 20-year extension. And so the amount of sea level rise by that time, maybe a foot, maybe under the worst case scenario that I was talking about, 3 feet by 2050. They should be in good shape then. I don't think we want a Seabrook nuclear power plant operating at 2100. I think that it begins to get a little dicier as you see those 1 in 1,000 chance of sea level going up 9 feet. In terms of what seacoast communities are doing, I've been part of the New Hampshire Coastal Adaptation work group for the last decade, and there is a lot of great work going on right now. So you look at the city of Portsmouth, which has a whole sustainability plan. They've looked at the impact of sea level rise on their heritage sites. They've looked at they've done the mapping on what areas are most vulnerable to flooding, what they need to start doing in the short term, and the medium term, and the long term. Seabrook and Hampton are arguably going to be the most affected by sea level rise. I mean, Hampton last year, I think, had over 50 days of clear sky flooding, which means they were getting flooded every week at high tide. And so they're beginning to have sort of very serious conversations, community conversations, which I would argue is exactly what needs to happen. The community needs to decide how it's going to adapt to these changes. The challenge there is that it's a really difficult conversation, and they're certainly able to buy some time. In the long term, it's going to be Hampton and Seabrook face some existential challenges, as does Rye, New Hampshire. There's a lot of work that's been done by the Rockingham Planning Commission on the future of Route 1, which, if you live on the coast, is the main north-south corridor. And if you've ever been there during a big nor'easter, they actually have huge plow trucks plowing rocks off the road that are getting thrown onto Route 1 by the waves. So there's significant challenges around Route 1, and Rockingham Planning Commission is just finishing up a study on sort of the future of Route 1 and how we're going to ensure that people can evacuate that region if and when is necessary. So I'd say there's lots of discussions. The New Hampshire Coastal Program is very active in identifying places that are most vulnerable and helping to address those challenges. There's also a lot of living shoreline projects that have been developed that sort of will help protect us from storm surge. And I would say with all that said, we're still in our infancy of dealing with the issue of a sea level rise in a really serious way. And the good news is we have some time. Even though there's flooding already, we have some time to deal with these challenges. But we're going to have to start working harder and harder at dealing with that.
Great. Thanks, Cam. Awesome
So,
answer. Go ahead, Susan.
What exactly do we need to do in terms of what percentage of carbon emissions need to be reduced at what speed to change these projections for rising temperature and rainfall?
You want to give it a go, Mary?
That's all right.
Serious reductions, right? So if you look across the US, we've seen a modest reduction in greenhouse gas emissions over the course of the past 20 years, but not a significant reduction. So the Intergovernmental Panel on Climate Change is essentially saying we need to get back down to zero emissions by 2050. So we need a complete well, not a complete because we've started, but we need a significant transformation of our energy system so that most of our energy is coming from non-carbon low carbon to no carbon forms of energy. So we're talking about wind and solar, and there's those that argue that we should have safe nuclear, although I think there's some questions on the extent to which that can happen economically. We clearly need to figure out how we store energy from renewables because we have to sort of flatten the curve, and I can talk about that. And then we're going to have to likely figure out ways that we can actually remove carbon dioxide either from the atmosphere or from power plants that still burn fossil fuels or that burn biomass energy. But that needs to be a much smaller part of the picture. We really need to get most of our energy from renewable sources, and we need to do that in less than 30 years.
Yeah. Great, thanks, Cam. By the way, I want to say one thing. You know, we at the New Hampshire Network, we've got plans for more events like this, specifically looking at adaptation and policy responses. And so we've got a couple of outstanding climatologists. I want to insert another quick question, which I'll direct at Mary primarily. In 1938. There was a cyclone that tracked way inland, unusually so. And I'm curious about when we look at well, historical and future modeling, historical records and future modeling. Is there anything that can be said about the likelihood of unusual storm tracks? Because I know that there's been a lot of work on whether there's going to be more storms or whether the storms that occur are likely to be stronger. But what about the tracking? Is there anything that can be said about that?
Yeah, first, do you want me to get this out of presentation mode?
Oh, yeah, why not? Sure.
Oh. Okay, yeah, and so as far as storms go, there is high confidence that storm intensity, particularly hurricane intensity, will increase. So the storms that are going to be coming at us, when they do, are likely to be stronger. And so where we are, if we're speaking of tropical storms and hurricanes specifically, we kind of benefit from our northern location because tropical cyclones tend to weaken as they go over colder water and weaken as they move over land. And most of those cyclones are going to come from the south, so they have to move over southern New England before they get to New England or to New Hampshire. So we benefit from that. But there are some modeling studies that are indicating, this is still kind of new stuff, indicating though that there will be, it's the possibility to have more storms that are going to be reaching the North Atlantic. And if there are more storms that are hurricane strike that make it that far north, that would increase our chances of having more hurricanes as opposed to maybe more tropical storms. So it's kind of everything is lifted up. Now, as far as the storm tracks, I don't think there's anything that's really high confidence, unless Cameron, if you've read anything new recently. But I have seen a few articles that have indicated that the North Atlantic might become a little busier as time goes on and ocean waters warm.
Mm-hmm. Yeah, great. All right, excellent. So John, you had a question. I think we've just got a few minutes left, but go for it.
Okay, well, this is from Vincent. And we have a broad spectrum of people here tonight. Not all of them are completely on board with the basic science. So we have an opportunity to hear from two of our state's leading scientists in the subject. What do you tell somebody who says things like correlation is not causation? Climate change is based on modeling, not science. I'm not trying to put you on the defense. I'm trying to, there's people that just don't trust this yet. Are there scientific organizations that say other things? What is your response to these kind of things?
Well, so I have so many different responses. One is that I also saw Vincent's comments in the chat, and having been in this field for over 20 years, I don't think Vincent has any interest in having a conversation with us. I think that he's just bringing out a lot of old tropes. So correlation is not causation is something that you can't graduate from an undergraduate degree in science without completely and utterly understanding. So the notion is that all we did was look at carbon dioxide is going up and the temperature is going up, and we stopped all our research there and said, look, carbon dioxide is causing climate change. So that's not what science has done. In fact, science has known for over a century that carbon dioxide traps long-wave radiation coming from the Earth, as does other greenhouse gases. And so that's sort of going back to first principles of understanding how molecules in the atmosphere interact with radiation coming from the planet. And then, you know, in my particular world, I'm a paleoclimatologist. And so most of my, in fact, the vast majority of my research has looked at how climate has changed in the past. And we don't model it, we actually collect records and we describe how it's changed. And then we look at different reasons on why it has changed. So that how and the why is a fundamental part of climate change. And climate change isn't something that like just happened with human beings, right? Earth's climate has always changed and it always will change. But there is this overwhelming body of scientific evidence that we've developed over the course of the past 30 years. And we've looked at every possible reason on why climate changes, right? From meteorite impacts, to changes in volcanic eruptions, to changes in solar energy, to changes in the position of continents, to changes in ocean circulation, you know, on and on. We sit around and we poke at each other's hypotheses and theories all the time. And the scientific community has now arrived at this conclusion that humans are very likely driving the increases in temperature. And in fact, every 5 years that the Intergovernmental Panel on Climate Change puts its report out, the evidence and the language gets much stronger. So there's a really good, very solid body of evidence that supports the points that Mary and I were making tonight. And really, I know of no international or national scientific body that would claim otherwise. So Mary, I don't know if you want to add your 2 cents to that.
Yeah, and maybe just reiterate the physical science basis for this. A lot of my early career in my dissertation, I actually ran climate models focusing on sea ice, and they're physically based. We understand the physics of a lot of this, and the physics that we don't understand, that's where this idea of uncertainty and why you see ranges of values being presented. And so the greater the uncertainty, the less we understand. And so, you know, again, there's a lot of physics behind this, and physics that we've known for a century or more.
Thank you very much, both
Yeah.
of you.
I'd like to add something quickly to that, which is that a lot of people don't realize that the first person who published an account of an experiment showing that carbon dioxide actually does raise the temperature, or that is to say, it retains energy, thus raising temperature, was Eunice Foote in Pennsylvania in 1856. She just took 2 flasks, one containing air and one containing a greater density of carbon dioxide, and put them on the windowsill where they were, where the sun was coming in, and then measured the temperature, and it was much higher in the one with the carbon dioxide. So I mean, we've known that on a physical basis for a very long time, so that's just to reinforce what Cam had to say.
May I ask one follow-up, Reinmar?
Go for it.
So how important is it for New Hampshire that the world reach net zero carbon emissions by 2050? Would it be, much different if we let it slide and instead of shooting for the 1.5 degree target, we shot for the 2 degree target or more?
I think that's a great question. We haven't done, we've showed you differences in sort of temperature based on different global climate scenarios. We haven't looked at specifically what the difference in the impacts in a 1.5 degrees Celsius to 2 degrees Celsius world would be, although I think that would be an interesting exercise. I guess that the thing I would say is that the IPCC has made it very clear that globally, there's really significant differences between a world that warms 1.5 and 2 degrees Celsius. And a lot of those differences will affect people in New Hampshire in a big way. But more importantly, they're actually going to affect almost everybody who lives on the planet. So if you think supply chains have been disrupted by COVID, you can think about how supply chains are going to be disrupted in a world where it's really difficult if you live in the tropics to grow the food to feed the population in the tropics. Or you think about all of the coral reefs dying, or you think about 1/3 of humanity is under the stress of excessive heat waves. John, I don't have the answer to your specific question, but I really think that it's the broader changes that happen globally are going to have a significant impact on everybody, including residents of New Hampshire.
And can I just add on to that real quick too? You can think about it, just in terms of your daily life. And, when our summers are hotter, there's not a lot of places with air conditioning. Well, places are going to have to get air conditioning soon. That's going to increase electricity needs, increase costs. And so there's this whole effect of how the changes at a seasonal level are going to impact, not just kind of in the large global sense, but just down to our daily lives.
Thank you.
Yeah. Thank you both so much for being here and sharing some of this scientific work with us. I think for the audience, New Hampshire Network, we are all about helping move policy changes forward. Let's put it that way. And so the science, whenever it gets presented in a clear, factual way, always throws up a lot of questions about how should we respond, how have we responded so far, and how should we respond in the future. And we will address some of those questions more specifically in upcoming presentations and events. And I hope that everyone on the call now will join us again in the future. And I'm just going to turn this over to Susan, who will talk a little bit about some of the specific events that are coming up. And I do want to end at 7, but let me just share the slide. Oh, that's actually not the right one. Sorry about that.
Well, I'll start talking.
Yeah, talk anyway.
Okay, so here we all are feeling glum and worried about the future, but John Gage has planned in 2 weeks from today, Monday, March 28th, to have a program about can we reach 2050 and what are some of the policies that can help to get us there. We'll have Dr. Charles Whelan, a policy expert from Dartmouth, speaking, but he won't quite have R2D2, but he'll have the MIT En-ROADS Climate Policy Simulator to help us actually see what deforestation versus reforestation, what effect that has, what effect more electric vehicles has. So that should be an informative and hopeful discussion and more based on policy, which I know a lot of people were asking questions about tonight. So that is 2 weeks from today, March 28th. And then the end of March is changeover day, crossover day in the legislature. And on April 11th, Joe Kwasnick is going to have a number of legislators from New Hampshire with him to discuss how changeover day works and what to look forward to or to cringe at. And he is titling the presentation, "The Beauties and Beasts of the Current Legislative Session." And then in the meantime, to have real conversations among ourselves, to dig in, to decide what's next, to help move things along. We have working groups, legislative working group, Joe Kwasnick leads, and a plastics working group that grew out of our last presentation, 10 Towns Toolkit. And there we have the beauties and the beasts of environmental bills at the crossover session. Let's see, Brian Mar, why don't you skip up one just to show, okay. So
Net zero.
Okay, so that is in 2 weeks, policy options to achieve the COP26 climate ambitions. And the graph you see on the left is a little picture of one of the models that the MIT En-ROADS will come up with as people from the audience suggest different possibilities. And then on April 11th is the discussion of crossover day at the legislature. And that's at 5:30. And then finally, the 2 work groups that we invite you to join. There we go. Plastics work group, next meeting, March 27th, legislation, next meeting, April, I can't see it. I think it's
12th.
the 12th. Thank you. But at the bottom of every screen is our website, www.newhampshirenetwork.org. If you go there, you'll get all the information you need and the links. So that's just one easy go-to place for finding out about any of these events. And thanks, everyone.
All right. Thank you so much, Susan. And thank you, everybody. Have a great rest of the evening. Sorry about that confusion there. I think that the lesson of that is to make sure that whoever's talking has control of the slides when possible. And we hope to see you all again very soon. Thank you for your attention.
Good night, everybody.
Good night. Take care.